Symmetry and Skew-Symmetry of a plus $A and a $A. Hello everyone. To begin this section, let's first look back at our foundation. In the previous subsections, we spent some time defining exactly what symmetric and skew-symmetric matrices are and how to identify them. Now, we are going to explore a fascinating property of square matrices. We will discover that any square matrix, which we will refer to as matrix A, can actually be used as a building block to generate both a symmetric matrix and a skew-symmetric matrix. The most interesting part is that we can achieve this simply by adding or subtracting the transpose of matrix A from the original matrix. Over the next few slides, we will look at the properties required for this and walk through the formal proofs to see why this always works. Prerequisite properties of transposes. Now that we have introduced the concept of generating symmetric and skew-symmetric matrices, before we dive into the actual proofs, let us recall three fundamental properties of the transpose of a matrix. It is important to keep these in mind, as these properties serve as the essential building blocks for the derivations we are about to perform in the upcoming slides. First, let's look at the transpose of a sum. This property states that the transpose of the sum of two matrices is equal to the sum of their individual transposes. In other words, the transpose of a plus B is equal to the transpose of a plus the transpose of B. Next, we have the double transpose property. This is a very straightforward rule. The transpose of a matrix brings us back to the original matrix itself. Simply put, the transpose of A is equal to A. Finally, we have the transpose of a difference. This follows a similar logic to the sum property, where the transpose of a minus B is equal to the transpose of a minus the transpose of B. Once you are comfortable with these three rules, we can move forward to prove our first theorem. Theorem 1, the symmetry of a plus $A. Now that we have refreshed our memory on the fundamental properties of transposes, let us move on to Theorem 1, which focuses on the symmetry of the sum of a matrix and its transpose. The statement of the theorem is as follows. For any square matrix A, the matrix formed by adding A to its transpose, a transpose, is always a symmetric matrix. To begin the proof, we must first recall the defining characteristic of a symmetric matrix. To prove that any matrix is symmetric, we must demonstrate that its transpose is exactly equal to the original matrix itself. Let us start by defining a new matrix, which we will call X, as the sum of matrix A and matrix A transpose. Now, our goal is to find the transpose of X to see if it returns us to our original expression. In step 1, we apply the transpose operator to both sides of our equation. This gives us X transpose equals the transpose of the quantity A plus a transpose. In step 2, we apply one of the prerequisite properties we discussed in the previous slide. Since the transpose of a sum is equal to the sum of the transposes, we can rewrite this as X transpose equals a transpose plus the transpose of a transpose. Moving to step 3, we use the double transpose property. As we know, taking the transpose of a transpose returns the matrix to its original form. Therefore, the transpose of a transpose is simply A. This simplifies our expression to X transpose equals a transpose plus A. In step 4, we utilize the fact that matrix addition is commutative. This means the order of addition does not change the result, so we can rewrite a transpose plus A as a plus A transpose. In step 5, if we observe our result, we can see that it is identical to the original matrix X that we defined at the start. Thus, we have shown that X transpose equals X. In conclusion, since we have proven that X transpose is equal to X, the matrix formed by a plus a transpose is officially a symmetric matrix. Once you have grasped this logic, you will find that the proof for skew-symmetric matrices, which we will cover in the next slide, follows a very similar mathematical flow. Theorem 2, the skew-symmetry of a $A. Now that we have established the symmetry of the sum of a matrix and its transpose, let us move on to Theorem 2, which explores the difference between the two. The statement for this theorem is that for any square matrix A, the matrix formed by subtracting its transpose from the original matrix, that is, a minus A transpose, is always a skew-symmetric matrix. To begin the proof, we must first recall the defining characteristic of a skew-symmetric matrix. To prove that a matrix is skew-symmetric, we must demonstrate that its transpose is equal to its negative. Let us start by defining a new matrix, which we will call Y, as the result of a minus A transpose. Now, our goal is to find the transpose of Y to see if it meets the condition for skew-symmetry. In step 1, we apply the transpose operator to both sides of our equation. This gives us Y transpose equals the transpose of the quantity A minus a transpose. In step 2, we apply one of the fundamental properties we reviewed in the prerequisite slide. The transpose of a difference is equal to the difference of the transposes. Therefore, Y transpose equals a transpose minus the transpose of a transpose. Moving to step 3, we use the double transpose property. As we previously discussed, the transpose of a transpose returns us to the original matrix. So, the expression simplifies to Y transpose equals a transpose minus A. In step 4, to make the expression more recognizable, we factor out a negative one from the terms. This reverses the signs within the parentheses, resulting in Y transpose equals negative of the quantity A minus a transpose. In step 5, we observe that the expression inside the parentheses is exactly our original matrix Y. Therefore, we arrive at the result that Y transpose equals negative Y. In conclusion, since we have proven that Y transpose equals negative Y, the matrix formed by a minus a transpose is officially a skew-symmetric matrix. Now that we have completed the theoretical proofs for both symmetry and skew-symmetry, let us proceed to the next slide to verify these results using a numerical example. Illustrative example. Now that we have established the theoretical proofs for both theorems, let us put them into practice with a concrete numerical example to see how these properties behave in real time. Let us start with a simple 2x2 square matrix, which we will be called matrix A matrix. A consists of the first row, 2 and 4, and the second row, 1 and 3. Step 1 is to find the transpose of A, which we denote as a transpose. By swapping the rows and columns, the first row becomes the first column, and the second row becomes the second column. This gives us a matrix where the first row is 2 and 1, and the second row is 4 and 3. Now, in step 2, we will verify the first theorem, that the sum of a matrix and its transpose is always symmetric. Let us define a new matrix, X, as the sum of A and a transpose. By adding the corresponding elements, 2 plus 2 gives us 4, 4 plus 1 gives us 5, 1 plus 4 gives us 5, and 3 plus 3 gives us 6. Thus, matrix X is a 2x2 matrix with the first row 4 and 5, and the second row 5 and 6. To verify if X is symmetric, we must check if X transpose is equal to X. If we take the transpose of matrix X, we find that the first row remains 4 and 5, and the second row remains 5 and 6. Since X transpose is identical to X, we have numerically confirmed that the result is indeed a symmetric matrix. Finally, in step 3, we will verify the second theorem regarding skew-symmetry. We will define a new matrix, Y, as the difference between A and a transpose. Performing the subtraction, 2 minus 2 is 0, 4 minus 1 is 3, 1 minus 4 is negative 3, and 3 minus 3 is 0. So, matrix Y has the first row, 0 and 3, and the second row, negative 3 and 0. To check for skew-symmetry, we need to see if Y transpose is equal to negative Y. First, let us find Y transpose by swapping the rows and columns. This gives us the first row, 0 and negative 3, and the second row, 3 and 0. Now, let us find negative Y by multiplying every element of matrix Y by negative 1. This results in a matrix with the first row, 0 and negative 3, and the second row, 3 and 0. As you can observe, Y transpose is exactly equal to negative, why this confirms that the matrix formed by a minus a transpose is skew-symmetric. This example perfectly illustrates the theorems we proved in the previous slides. In the next section, we will summarize the key takeaways and discuss some common mistakes to avoid when performing these calculations. Key takeaways. Now that we have walked through the formal proofs and verified them with a numerical example, let us summarize the key takeaways from this lesson. First, as we have demonstrated, the sum of any square matrix A and its transpose, a transpose, will always result in a symmetric matrix. Similarly, the difference between a square matrix A and its transpose, a transpose, will always result in a skew-symmetric matrix. It is important to remember that the proofs we performed in the previous slides rely heavily on two fundamental properties. First, that the transpose of the sum of two matrices is equal to the sum of their individual transposes, and second, that the transpose of a transpose simply returns the original matrix, A. One final observation to keep in mind is that in any skew-symmetric matrix generated by the operation A minus A transpose, the diagonal elements will always be 0. This is a useful characteristic to check when you are solving these problems. Now, to ensure you don't lose marks on these concepts, let's move to the final slide and discuss some common mistakes to avoid. Common mistakes. Now that we have covered the theorems and seen a practical example, let's wrap up by discussing some common mistakes students often make so that you can avoid them in your exams. First, be very mindful of sign errors during subtraction. When you are calculating a minus A transpose, it is quite common to make mistakes when subtracting elements that are already negative. To prevent this, I highly recommend always using brackets when subtracting matrices to ensure your signs remain correct. Second, be careful not to confuse symmetry with skew-symmetry. As we established in our proofs, for a matrix to be symmetric, we are looking for the transpose to be exactly equal to the original matrix, which we represented as X transpose equals X. However, for skew-symmetry, the condition is different. We must show that the transpose is equal to the negative of the original matrix, or Y transpose equals negative Y. Third, do not overlook the double transpose property. A frequent error is forgetting that taking the transpose of a transpose returns you to the original matrix, meaning a transpose equals A. This is a critical step. Without this property, the proofs we discussed in the previous slides cannot be completed. Finally, remember that these properties apply exclusively to square matrices. You cannot find the sum of A plus A transpose if it is not a square matrix. This is because the dimensions of the original matrix and its transpose would be different, and as you know, matrix addition is only possible when the dimensions are identical.